Hello everyone, my name is Naveed Anwar and I'm going to talk about HarvOS, efficient code instrumentation for transiently powered embedded sensing. This is a joint work with Luca Matola. 35 billion. That's the total number of sensors we are going to have by 2018 deployed under different applications like traffic management, automated manufacturing, wastewater treatment, smart parking solution, and smart streetlights. Just to give you the scale of this number, the total human population in the same year will be 7.7 billion, which is 5 times less than the total number of sensors we are going to have in the same year. And the growth of these sensors is expected to increase by 200%. These numbers are really huge. However, it is possible that this growth might get limited because of the way these devices are powered. What I mean is they are either being hardwired, so there is an installation cost, and in some scenarios that's not even possible, or they are powered through batteries. But then who is going to replace those 35 billion batteries when they are going to die? So there is a huge maintenance cost. The potential long-term solution to this problem is energy harvesting. However, energy harvesting has its own drawbacks. Normally, the energy which you harvest from these mechanisms is highly variable and unpredictable. And because of this unpredictability, these batteryless devices continuously reboot and loses their state, which not only wastes time, but also energy. And in some extreme cases, these devices are not even able to complete their tasks. Researchers are trying to make these batteryless devices immune to transient power environments through state retention solution. Just to give you an idea of how state retention works, this is a basic illustration of batteryless embedded devices working in energy harvesting environment. First, they harvest energy up to some reasonable voltage level, then they do some processing, and when the energy drops below the operating voltage, the device shuts down. In state retention solution, you save the state of the device whenever it's about to die and later restore the state when it has enough energy. However, within the state retention solution, there are two problems which are not fully explored, and I am going to explain you through an analogy. Consider yourself as a treasure hunter who knows that there is a gold on top of this mountain. You want to go up there as quickly as possible so that you can claim all the gold. There are two refreshment shops in your path. You skip the first one because you didn't feel thirsty or hungry at that moment, but later at some point you realize that you don't have enough stamina to go any further. Your death is inevitable and that goal is now a far-fetched dream. Same kind of problem happened with these batteryless devices. This person is actually a batteryless sensor, this mountain is an application progress, and these refreshment shops are the trigger calls which provides opportunity for the device to save its state. And this is the point where the device loses all its power. So the question is, when and where should we checkpoint the state of the device? The question is challenging because in order to answer it, we need to achieve two goals. The first goal is to minimize the number of trigger calls because trigger calls need to probe energy buffer, which not only consume energy but also changes the execution time. And the second goal is to postpone the actual checkpoint to the last moment, because doing checkpointing too early could waste energy that could be usefully employed in later computation. The challenge here is that both these goals contradict each other, because postponing the checkpoint in fact requires frequent checks. So what we want is to come up with a solution that can perfectly balance these trade-offs. We have designed a software-based solution, HarvOS, which does not require any hardware modifications in the existing system. It automatically places the trigger calls within the user code and decides whether to perform the checkpoint before continuing the execution or not based on the remaining energy in the buffer. It consists of 4 basic steps. At first step, we compute the control flow graph of the program and associate every path in the graph with the energy required to execute it with the target MCU. Next, we estimate the maximum number of useful cycles a device can run when its energy buffer is fully charged. For simplicity, we are going to consider linear control flow graph. We will discuss the general case in later slides. At step 2, we split the control flow graph in subgraphs whose total stretch in number of cycles is at most CUs by 2. Then, At step 3, within each subgraph, we identify the block corresponding to the minimum size of allocated memory and place a trigger call right at the end of it. We do this because we want to reduce the cost of the checkpoint operation, as the amount of data to copy over a stable storage is minimal at this point within the subgraph. Also, because of our placement strategy, the maximum number of MCU cycles separating any two trigger calls, for example trigger call 1 and trigger call 2, is bound to be less than CUs, which is the maximum number of cycles MCU can execute within the single charge. Step 4 executes at runtime, where at every trigger call, the system takes an informed decision on whether to checkpoint or not. As intuitively shown in this diagram, the system basically checks if the remaining energy is sufficient to reach the next trigger call and to checkpoint there. If the remaining energy is less, then the system will checkpoint the state. Otherwise, it will carry on the execution. However, control flow graphs are generally not linear, as in the example we just discussed now. They actually consist of complex structures reflecting a variety of available programming constructs. We identify branches, loops, function calls, and interrupt handlers as the fundamental structure of the control flow graph and design specific rules for them. These rules are recursively applied on the control flow graph until an elementary block in the control flow graph is reached. First, we are going to discuss branches. The challenge here is to account for the lack of compile time information on what path is taken at runtime. We can instrument the code to trace the actual execution, but it will add further overhead and greatly complicate the instrumentation strategy. Also, as the complexity of the code grows, the number of possible paths also increases exponentially, which can further complicate the instrumentation strategy. So we used a worst case approach and avoided any further code instrumentation besides the trigger call. Within the branch, there are two cases. In the first case, the minimum amount of allocated memory is outside the branching statement, for example, at location T1. In this case, at trigger call TA, we consider the eNext value corresponding to the most energy consuming branch. At T1, we will probe the energy buffer to find out the exact value of E remaining before taking a decision to checkpoint. The second case is when the minimum amount of allocated memory is found in either of the two branches, say at location T1. However, an issue arises if the other path is taken where no trigger calls are placed. To cater for this, we place a trigger call right outside the branching statement at location T2. The eNext value at trigger call TA is set to the most energy consuming path between those leading to either T1 or T2. At T1, we can spare probing the energy buffer because provided only one execution path exists between TA and T1. At T2, we still need to probe the energy buffer. Same set of rules can be applied when the branching is spread across multiple subgraphs. In case of loops, the challenge arises if the number of iterations are determined at runtime. In such a scenario, we need to decide whether the trigger call inside the loop, for example T1, should consider the eNext value to reach the first trigger call inside the same loop when the loop continues with the next iteration, or consider the eNext value to reach the first trigger call outside the loop, for example TB, when the execution exits the loop. We choose the first option because of two reasons. Number one, loops that depends on runtime informations are likely to yield at least some number of iterations. And number two, if we consider the second option, then we will continuously overestimate the eNext value and may perform early checkpoints, which is against our goals. In case of option 1, we only need to place another trigger call T2 right outside the loop because we have no information on how many loops iterations executed before exiting the loop, and it will probe the energy buffer. In case of functions, the situation is equivalent to inlining the control flow graph of the function within the control flow graph of the caller, as shown here. However, the challenge here is that same function can be called at multiple places in the code. Therefore, at the first trigger call, we need to probe the energy buffer, as the function's execution is unaware of where the caller code issued the call. Thus, we cannot know what is the amount of energy spent since an arbitrary trigger call TA. And because of the same reason, we need to place an additional trigger call right after the function returns, indicated with tReturn trigger call. The case of interrupts adds another challenge to those for the function calls. The challenge here is that system has no information on what was the situation in the execution when the handler was preempted. It can be called from anywhere within the code. In order to handle this case, we need two additional rules to those discussed in the last few slides. As the interrupt handler has no information on what decision was taken at the last trigger call TA, we place a trigger call right at the beginning of the interrupt handler to verify that the next trigger call within the interrupt handler is reachable. Thus, probing the energy buffer is mandatory at trigger call T1. Second, when the interrupt handler finishes, it has no information on where the next trigger call is located in the main code. It may happen that the execution at trigger call TA was actually expecting to checkpoint at trigger call T3. As the interrupt handler consumes some amount of energy, T3 may be unreachable now and we need to checkpoint before returning to the main code. To capture this situation, every trigger call raises a flag if it expects to checkpoint at immediately following trigger call. In this example, TA would raise the trigger flag and the flag prompts an additional trigger call at the end of the interrupt handler to checkpoint. Finally, we need a second flag to indicate that the main code was preempted and T3 now needs to probe the energy buffer to update the remaining energy. So these are the four fundamental structures which we handle, and you can see here that we are not only trying to reduce the checkpoints but also the ADC operations by avoiding the energy probing of the buffer as much as we can. We evaluate the effectiveness of HarvOS on publicly available C implementations of Kalman filter, FIR filter, and advanced encryption standard. These applications include a variety of branching statements, loops, and function calls. Therefore, they exercise most of the trigger placement rule which we discussed in last few slides. These implementations have also different degree of complexity, with the Kalman filter code being the simplest, FIR filter code being the longest in number of lines of C code, and AES implementation being the one structurally most complex. Hardware-wise, we consider an ARM Cortex-M3 MCU on top of ST Nucleo board equipped with a standard flash as a stable storage. Here we are only interested on supporting transiently powered computing for the main MCU. Other components on the device such as sensors or radios can operate through separate energy buffer or techniques such as backscatter radios. We synthetically emulate the execution of the code and compute three key metrics. The number of times the MCU resets. This figure is inversely proportional to the effectiveness of a given instrumentation strategy. Given a fixed workload, the more the MCU needs to reboot, the more the checkpointing operation is subtracting energy from useful computation. The number of wasted cycles because the MCU exhausts the energy before reaching the next trigger call. This figure is again inversely proportional to the effectiveness of the solution. The higher is this value, the more a given instrumentation strategy is failing in accurately identifying the last useful moment where to possibly checkpoint. The minimum size of the energy buffer that allows the MCU to complete the workload under a given instrumentation strategy. For example, depending on how the trigger calls are placed, with small capacitor size, the execution may not reach even the first trigger call. This means checkpointing never happens and the system is stuck in a live lock situation, rebooting every time from the initial state. We consider the loop latch and function return strategies of Mementos as the representative of current approaches. In loop latch mode, Mementos places a trigger call at each loop latch, and in function return mode, it places a trigger call right after the function returns. Note that the voltage threshold which Mementos considers to decide whether to checkpoint is the result of repeated emulation experiments ran with specific application code and user-supplied energy traces. HarvOS does not require users to supply these energy traces, which may be hard to obtain in the first place. Our solution is rather based on the worst case analysis and assumes that the environment provides no additional energy once the device reboots. To study the performance of mementos in a manner orthogonal to the availability of energy traces, in our experiments we manually vary the value of mementos voltage threshold. In addition to mementos, we apply a brute force search on all possible executions of the code to identify an oracle that knows the last practical point in the time when to checkpoint. This is not feasible in reality because in order to do this, you need to place a trigger call after every instruction in the code, which may yield an unbearable overhead. These graphs shows the number of times MCU resets under all three applications with different instrumentation strategies including HarvOS and Oracle. We ran the memento strategies under two different voltages, 2.2 and 2.4 voltage. On x-axis we vary the capacitor size and y-axis shows the number of resets. As you can see in these graphs, bigger capacitor sizes generally corresponds to fewer resets because they have more energy for the computation. Compared to either of the memento strategies, HarvOS completes the fixed workload with 69% fewer resets on average, with a peak improvement of 80% fewer resets. Moreover, as you can see in these graphs, in most cases the performance of our solution rests very close to the oracle. Here we show the number of wasted cycles against the capacitor size. These graphs does not have oracle in them because oracle does not waste any cycle. As you can see in these graphs, at higher threshold voltages, mementos waste a higher number of cycles because checkpoints tend to happen too early in them, leaving unused energy in the buffer. Moreover, the staircase pattern in mementos, which is especially visible in Kalman filter and FIR filter graphs, appear because both its strategies are too coarse-grained. Either the trigger call is placed at the right place and so there are only few wasted cycles, or it is placed totally at the wrong point, so a lot of unused energy remains in the buffer. In fact, mementos placement strategies only look at the structure of the code and not its energy consumption pattern. These graphs shows the minimum capacitor size required to complete three benchmarks against different threshold voltages for mementos. On x-axis we change the voltage threshold and y-axis shows us the minimum capacitor size. As shown in these graphs, when operated under lower threshold voltages, mementos finishes the execution only with the bigger capacitors. This is essentially a result of its logic for placing triggers without reasoning on the energy necessary to reach the next trigger call. In contrast, our solution is independent of the voltage threshold and allows one to employ even smaller capacitor because we make decision on whether to continue the execution or to checkpoint based on the ability to reach the next trigger call. So in conclusion, our technique allows transiently powered embedded devices to complete given workload with 68% fewer resets from the state of the art, and it is at most 90% far from the oracle. In future, we are planning to explore the trade-off between simplicity of instrumentation and the additional information it can provide with a slightly bigger overhead. So this is the end of our presentation. If you want any more information, please visit our website nestlab.it, and thank you for your time.